Welcome to Lecture 24 in this series of modules on statistical process improvement and statistical quality assurance. We've come to the part of this course that has to do with so-called control charting. It's the part of the course that is technically closest to so-called statistical process control. I would really prefer to call it statistical process monitoring because this word control has connotations of process tweaking, whereas really what we're going to talk about here is not tweaking or adjusting, but rather simply monitoring. The context is this six-step quality assurance cycle of Barteman and Joe, and in particular, step 4, this assessing and working toward process stability, where the tools are the tools of control charts. The picture of what we're going to discuss here is one that one might think of in this cartoon way. Here's an eyeball watching what's going on in a process through some kind of a measurement system. A measurement system functions as one's eyeglass or one's magnifying glass for watching what's going on. A process is producing items sequentially or measurements sequentially, and there's some kind of a change. And the point of SPC, or really SPM, is watching processes for purposes of detection of change. One famous statistician has called SPC really nothing more or nothing less than organized attention to process data with the purpose of change detection. The history of control charting goes back to a man named Walter Shewhart, who worked at Bell Labs in the late 1920s and early 1930s. And he had this grand conceptualization. He thought, well, in observing process data, overall observed variation might be decomposed into two parts, into a baseline part and a part that might be eliminated. That baseline part one might think of as inherent to a particular system configuration. One might say that it's due to system or common or universal causes. Think of it as completely unpredictable, random variation. Temporally, one might think of it as short-term variation. The second kind of variation is variation that is potentially eliminated, and that variation might be due not to common or universal causes, but particular or special causes that have to do with particular or special circumstances. One might think of them then as think of it as non-random variation or long-term variation. If one accepts this conceptualization of Shewhart, the question is, how does one detect this second kind of variation that can be eliminated, so that one can intervene wisely, find reasons for process instability, process change, and eliminate it, leaving a process that one might call physically stable over time. Now, stability over time is not complete lack of variation. That's too much to hope for, but rather it's variation that is consistent in its pattern. And the point of Shewhart control charting is to provide a detection tool that allows one to recognize variation that is potentially that could potentially be eliminated, and to intervene, take action on that information. Shewhart's basic idea was to periodically, that is over time, take samples from a process and computes some summary measure, compute some statistic for summarizing process behavior. Plot that summary statistic over time and compare the plotted values to so-called control limits. If one makes a rather generic picture of this kind of thing, here's a time axis, here's an axis on which I might plot some, that gives values of some statistic Q. Q might be an average or a standard deviation or a range or a sample proportion. Plotting over time, period to period, I might see these values of Q rise and fall, but I'll only decide that there is variation that is more than baseline variation when a plotted value falls outside of so-called control limits. Points plotting outside of those limits indicate the presence of variation of the second kind and indicate the need then for physical intervention. Basic question that this raises is, where in the world did one get these control limits, the lower control limit and the upper control limit? Shewhart's answer was essentially this. If one thinks about individual observations from a process under stable conditions as being random draws from a fixed universe, then sometimes you can apply probability theory to produce a distribution for a plotted statistic that has a mean that can be calculated and a standard deviation that can be calculated. If most of a distribution, typically most of a distribution is within 3 standard deviations of its mean, so that if this mu and this q, this mu and this sigma are stable process means and mean and standard deviation for what's going to be plotted, one might take a mean plus 3 standard deviations and a mean minus 3 standard deviations and use them respectively for the upper and lower control limits for Shewhart control charting for deciding whether a process is stable or is not stable. To make this concrete, one might think of the case of a sample mean, where one is going to make n measurements and process them into an X bar. If individuals that are being averaged can be thought of as random draws from a process distribution that has mean mu and standard deviation sigma, then basic elementary probability says that X bar has a distribution with mean for X bar that is actually the process mean, and a standard deviation for X bar that is process standard deviation over the square root of the sample size. Using those ideas, one can take mean for X bar, which is process mean, plus 3 standard deviations for X bar, which is process standard deviation over root n, and make an upper control limit. Taking mean for X bar minus 3 standard deviations for X bar, one has a lower control limit. That calculation illustrates that very often process parameters, numbers that describe a data generating mechanism, appear in formulas for control limits, and you've got to have values from them, values for them that have to come from somewhere. There are basically 2 possibilities. Sometimes past experience with a process will give one an idea of what a what process parameters are, what an average is, what a standard deviation is. If I'm making a machine part, I might have a diameter, and I know that if I run a lathe in a particular way, I get a particular mean and a particular standard deviation. That's what we'll call a standards given situation, based on past experience. In other circumstances, one doesn't have past experience and is just presented with a series of samples, and the question, is it plausible that the process was physically stable over the period represented by the data? And we're going to call that an as-past data or retrospective scenario. When one is faced with an as-past data or retrospective scenario, really all that one can do is to tentatively assume that the process is stable, was stable, make provisional estimates of process parameters and plug them into formulas for control limits, and then apply those limits to the data in hand as a means of criticizing the provisional assumption of stability that was made in the first place. If data are all within those provisional, all within those as-past data control limits, then one comes to the conclusion that it was plausible indeed to assume that the process was stable. If there are points outside of those retrospective control limits, then there's no single set of parameters that could have generated the data in hand. In a standards given context, each new sample that one sees, one is essentially in real time asking, are process parameters currently at their standard values? That's a real-time kind of question. In a retrospective context, one doesn't operate in real time. One waits until one has, say, 20 or 25 time periods, and then looks back over the data from those time periods and asks the question, are these data consistent with any fixed set of process parameters? Not standard values for process parameters, but is there any set of process parameters at all that could have generated the cues, the statistics that we're observing? The standards given context is the most important of these two contexts. It has to do with real applications, real-time process monitoring. As a student, if you go and look in textbooks, they're going to be full not of the first kind of problem, but of the second kind of problem. Because, of course, if I'm going to give you data, it's not coming in real time. It has to be a retrospective problem. Nevertheless, the important application is to the first of these scenarios, not to the second.